Hey everybody, welcome to AlgoExpert. In this video, we're going to be covering the Knuth-Morris-Pratt algorithm, or the KMP algorithm. This is an extremely difficult algorithm, but one that is really cool, because it takes a pretty simple, well-known problem, string matching, looking for one string within another string, and it solves it very efficiently using pretty clever techniques that you may have even sort of thought of but never been able to sort of put into practice. So before we dive into the KMP algorithm and how it works, let's look at your typical string matching algorithm. Typically, if you've got two strings, like the ones that I have in front of me, this one here at the top, bunch of seemingly random letters, and this substring here, or potential substring, the way that you would implement an algorithm to find or naively find whether or not this substring is contained in this bigger string is by comparing every character one at a time, and whenever you get a failure, restarting. So you would start by saying, hey, take the first character of the big string, which is an A, compare it to the first character in the substring. Okay, they match, great. So move forward, compare the second characters together, they match. The third characters, two Fs, they match. Then you move on to the fourth, they match. The fifth, they're good. And then finally at the sixth characters, you see that F is not equal to D. And so in a sort of naive string matching algorithm that you've probably all implemented before with like double for loops, you would just immediately say, okay, we don't have a match here, so we're going to go back all the way to the beginning of the substring. So we're going to go back all the way back to the first letter, and we're going to move to the second letter in the main string and recheck whether or not our substring kind of starts here. And here we would see no, E is not equal to A, so we would move forward. Whoops. Let me just erase this. We would move forward to the F, compare the F to the A, no, not equal, and so on and so forth. Then you'd compare this A, this would be equal, and you would redo this over and over again. And so the time complexity of some naive implementation like that is going to be O of n times m, where n is the length of one of the strings, let's say the bigger string, and m is the length of the other string, the smaller string. And this, again, is implemented very easily with two for loops. Now, what the KMP algorithm does is it allows you to solve this problem of string matching, not in O of nm time, but rather in O of n, or rather O of n plus m time. So you can turn this multiplication here into an addition. And so you can imagine for huge strings, this is going to be super helpful. Now, how does it do that? Well, it takes advantage of the fact that there are oftentimes patterns in strings, and especially in strings that have repeated letters. And here is sort of a practical example that I can think of is, imagine genetics, the field of genetics, and like strands of DNA or something like that. You can imagine that there would be a bunch of repeated letters in string representations of these kinds of things, and if you've got billions upon billions of them, you might be able to do some clever pattern matching or pattern recognition to do your string matching. And this is what KMP algorithm is going to do. Looking back at our two strings here, what I want us to notice is that when we were doing the naive algorithm, the naive check of just checking every letter, and we got to the point where this F here didn't match this D here, we said, okay, we're going to go all the way back to the second letter of the main string, right? We were at the F, it didn't match the D, so we brought it back to this E, okay? And then we restarted by moving this here. But as sort of human beings, we can see that even though this F didn't match this D, we had the string or the substring AEF here that happens to be at the beginning of our string that we're looking for, the substring. So why did we have to redo or start to recheck all the letters all the way back here, the second letter, when we immediately saw that, oh wait, there's already a little pattern here that's been matched, and we don't actually need to move back to the second letter. All that we need to do is move forward one letter here and move this here right after the AEF. And we would be good. We could continue checking, right? So again, as humans, we can kind of see that. And to be honest, I would wager that a lot of you have kind of thought of that in your spare time, or the last time you dabbled with string matching algorithms. You've probably thought, isn't there a way to kind of keep track of letters that I've already visited that have kind of formed patterns where I can see that they're already repeating, and use that to our advantage, right, to come up with an optimal algorithm. So with that, everything that I just said is kind of the tease for what the KMP algorithm is and how it works. Let's actually dive into it and see the implementation. Perhaps the best way to do this will be to just go through it with an example and explain it as I go. And I'm going to do that with these two strings that we've been playing with. So we've got this long string here, this smaller string here, and the reason I've got the word true written here is just to say that this substring is indeed contained in this bigger string, and it's contained here at the very end, right? So this is where it starts, AEF AE, D AEF AE FA. How do we find that? So the first thing that we're going to do with the KMP algorithm is we're going to disregard the bigger string for a second, and we're going to traverse our substring, the string that we're looking for, and we're going to build a table, or basically an array, a list, a one-dimensional list, that is going to keep track of patterns that we identify in the substring. So let me explain, let me demonstrate. We're going to start by putting declaring two indices that we're going to use to traverse this substring, and these two indices are going to be I and j. So I'll write I in green, and I'll initialize it at index 1, so I'll put it under index 1 here, and I'll put j at index 0, okay? And perhaps just to help us visualize this better, or to help us go through this faster, I'm going to write the indices of every letter or every character in the string above each character. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 12 character string. Or, sorry, 13 character string. Now, we're also going to start creating our table, right, which I'll denote like this. And this table is going to be initialized to a bunch of negative ones. I'll get into what those negative ones mean in a second, but for now, just imagine that it's a bunch of negative ones here. And I'll probably just fill them in as I go. So now the first thing we do is we compare the two letters in our string that we're looking for at index I and at index j. So we compare the letter at index I against the letter at index j, and we check whether or not they're equal. Right now, these two letters aren't equal. So I'm just going to say, okay, I'll leave a negative 1 here and here, so at both letters. let me erase that and rewrite it. -1, -1. And I'm going to increment my I index by 1. So now I points to index 2 and the letter F. So what do these -1s mean? Well, they mean that at the given index here, so 0 and 1, we don't have any patterns. We have not identified that the letters A or E or any patterns within them appeared before in the substring. And so you can imagine that for the first index, index 0, it's always going to be -1 because this A here doesn't belong anywhere. Or this is A is the first character in the string, so it can't have appeared before. There can't have been a pattern before it. So now we get to this F, okay? Compare the F, again, to the letter where J is, which is A. They're not equal to each other, so we're going to put -1, and we're going to grab the I and move it to the right. This is where things get interesting. So we compare the letter at index I in our string, which is A, to the letter at index J in our string, which is also A. And we see that, of course, A is equal to A. So what that means is, in the substring so far, AEFA, we've identified a pattern. This pattern is very simple. It only consists of one letter so far, the letter A. But we've identified that pattern. In some sense, we can say that we've got a prefix in this string or substring AEFA that is also a suffix, right? This letter A is not only a prefix but also a suffix. And so when we're at this index here, I, which is 3, we can say where is the last time that this sort of pattern appeared? It's at index J, which is 0. Okay? And so we're going to mark that. So I'm going to write down 0 here. Okay? And now what we're going to do is we're going to move both I and J to the right. Okay? So instead of moving just I to the right, because I was equal, or the letter at index I was equal to the letter at index J, we move both of them. And now we continue to compare the characters. So the letter at index I in the substring is E, and the letter at index J in the substring is also E. E is equal to E. So what do? Well, we say there's a pattern in this substring so far here, AEFAE. There's a pattern that we've recognized, and it's saying that at index E, right, the pattern, at index I, where this letter E is, the pattern matches whatever pattern we have ending at index J. Index J is 1, so we're going to mark 1 here. So basically, whenever we get a letter that matches another letter, right, we say, hey, at index I in the pattern table, we're going to store index J. And again, it's saying that there's a prefix here that ends at index J that is also a suffix in this substring, right? And so we store it. Again, right now this might be a little bit confusing, but bear with me and it'll start to make more sense. Whoops, let me just erase this purple here. Okay, so now we're gonna move both the indices J and I, because again they were equal to each other. So we'll move both of them. And now this is where things get interesting again. We've got F and D. These two letters are not equal to each other, right? They're not equal to each other, but J is greater than 0. J is equal to index 2 right now. So we're going to say, let's check the letter right before where our index j is, which is here, this E, right? And let's see if this E had a pattern that it had stored that we could use to compare against. So we look in our table at index j minus 1, which is here, right? J is equal to 2, minus 1 is equal to 1, and there's a negative 1 here. So we just reset j to 0. Okay? So what this means here, this is really important. What this means is that this D here, basically, or rather this substring here, AEFAED, there is no pattern that we've identified in this substring that ends with D and that has like repeated characters at the beginning. There is no prefix in this substring that is also a suffix of this substring. Okay? And visually, the way you can kind of think about it is, look, there's no pattern here, right? Like this AED or ED or whatever is just not here. It's not in this substring anywhere but at the end. Okay? So we're going to put a negative 1 here for this index 5 above the D, and we're going to keep moving forward. I'm going to erase this purple, and now I'm just going to move my I forward 1. Okay, so now things are going to get really interesting, and things are going to start making sense, because right now you might be thinking, I still don't really get what these numbers represent. What are they doing here? So compare the letter A here at index 6 to the letter A here at index 0. These two letters are equal. So we're going to mark a 0 here. Again, this tells us that basically in this substring, AEFAEDA, there is a prefix that is also a suffix. It happens to be just the letter A. And so we're going to denote that by saying, hey, at this index 6, we know that the prefix ending at index 0 is also a suffix, and it's a pattern that we've identified. Okay, we're marking it here, and now we grab both of our indices and move them to the right. These two E's are equal to each other, so we're going to say, okay, at index I in our table here, we're going to put index j, which is 1, and we'll put it here. Again, what does this mean? It means that in this substring, AEFAEDAE, we've got two patterns, or one pattern rather, where a prefix AE is also a suffix here. Okay? Again, we're going to see what that means in a second. So now we move our two indices forward one more. F is equal to F, so we're going to put a 2 here. Move our indices one more. So now we're comparing A to A. They're equal to each other. Great. So we're going to put a 3 here because J is index 3. So now we're going to move J under this E and I under this E as well. These are once again equal to each other. So we're going to put a 4 here. To take a little pause, again, what this means is in this substring here, AEF, AED, AEF, AE, it's a mouthful, we've got at this index 10 here, we put index 4, which is J, which told us that there's a prefix ending at index 4, this prefix, right, AEFAE, that is also a suffix, AEFAE, right? And now this is where things are going to get interesting. We move index J one more to the right, we move index I one more to the right, and here, this F is not equal to this D, right? And now we're going to see the pattern come into play really well. This F is not equal to this D, right? We can all agree on that. But there are clear patterns in this substring. So what we're going to do is we're going to say, well, look at the letter immediately before our current J letter. So this E. So basically I'll write maybe in brown a J here to say, look at the letter right before the one that didn't match, right? Our D here didn't match our F. Look one index to the left and see if here we've got a pattern. So look right below in the table, and we see that we've got a pattern ending at index 1. We've got a prefix ending at index 1 that was also equal to this suffix, right? So what this tells us is if we put our J, right, to this index 1 here, it is exactly the same as whatever we had here, right? This is exactly the same as this, okay? We failed our match at this D, the letter that came right after this sort of pattern here, this suffix. So what if we just went to the last previous matching pattern of this, which is this AE, and look at the letter that comes right after it, this letter, and check it against our current letter at index I, right? Because here, again, and this is where I'm going to repeat myself, because this is really the tough part of the algorithm, we were, I'm going to erase everything, we were here. Our index J was under the letter D. We compared this letter to this letter F at index I, knowing that everything that came before it, all of this, was equal to all of this, right? This failed. The D wasn't equal to the F. So now, instead of bringing our J all the way back to the beginning, we can say, well, wait, right before this D, where were we at? We were at this E here, and we know that this E matched a pattern at index 1. So everything that came before index 1 matched a pattern here leading up to this E. So this letter that we're comparing to this F, we could also compare this letter, which comes after something that's matching this AE here, and compare this letter to here. So that's exactly what we're going to do. We're going to say J, this J, is going to be equal to whatever is stored in our pattern one index before J, so here, the letter right before index J, which is this E. Let's see what pattern it matches. It matches the pattern at index 1, right? So we go here, down here, up here, and then we say let's go to the letter immediately to the right. So our J, all that to say that our J is going to move to this E, down here, boom, and under this F. And now we're going to compare this F to this letter. And here we've got F equal to F, and so we can mark index 2 here under this I and under this F, which means that in this substring, we've got a prefix ending at index 2 that matches a suffix, right, of 2 plus 1 characters, 3 characters. And then finally, right, we can move our J 1 forward, we can move our I 1 forward, and we see that this A is equal to this A, and so we can put a 3 here. And now we're done because our I is past the length of the substring, right? Typically we would increase the j here, increase the I here, and now we're sort of done with the substring. So what does this tell us, okay? I'm going to rewrite these numbers that we have, and I'm going to erase this true here. I'm going to rewrite these numbers under each letter. So -1, -1, -1, 0, 1, -1, 0, 1, 2, 3, 4, 2, 3. What do these numbers represent? Well, they represent the indices at which we've found matching patterns, and we've stored those indices such that we don't have to go back all the way to the beginning of our substring. Whenever there's a failure in a match, we can just go back to the last sort of matching pattern, right? So you can see that it makes sense that this A, E, and F would have a -1 because there is no matching pattern here, right? At no point in A, E, F do we find these letters at any time, right? Then we get to this A, and we clearly see that, hey, this A appears at index 0. Then we get to this E, and we clearly see that AE, this substring AE, appears at indices 0, 1, ending in 1, right? Then the D doesn't appear anywhere, so -1. Then we have A, again 0, E, AE, 0, 1, F, AEF, AEF, 0, 1, 2, 3, 4, because we have another A and another E. And then here, this F, let me circle it, right? This F, so we have AEF, AE, which is at the beginning here, but then this F here is not equal to D, so we can't sort of extend this substring like this. But what we can say is, well, wait a second, this F, when we were matching this F against this D, right, this E here, AE, had a pattern previously ending at index 1. So if we go to index 1, right, AE, the next letter might match this F. And so we compare this F, and we see that they're equal to each other. And so now this 2 here tells us that we've got a substring ending at index 2 that matches right here. And then similarly, this 3 tells us the same thing with index 3. Okay, so that was a lot to digest. Hopefully this starts to make more sense, what we're building here with this pattern. Now let's actually see how we can match against our real string. And then once we figure that out, we'll go through the complexity analysis of the question. So you'll notice that to match against the real string, and I'm going to give myself a bit of space, I'm going to move this down. To match against the real string, we're going to employ a very similar technique that we used when we were doing the pattern building. So let me actually also grab these indices and move them below our letters. And so what we're going to do is we're going to put index I now in our actual, we're going to put index I in our actual string, and we're going to put index j in our substring. So index I is going to be here, and index j is going to be here. And we're going to start comparing our letters, right? Start comparing the letter in the real string, or in the big string at index I, to the letter in the substring, or potential substring at index j. We see that they're equal to each other, right? A is equal to A. So we're just going to move forward. We're going to say, let's move this I here, and let's move this j here. So long as j is not at the very end of our substring, clearly we haven't found our entire substring. Once it gets here, then we've found, if it does, then we'll have found our entire substring in the main string. Okay, so now we keep comparing. E is equal to E, so we keep moving forward. grab this I, move it forward, grab this J, move it forward. F is equal to F, great. Move them forward, move them forward. A is equal to A, awesome. Move them forward, move them forward. This is getting kind of boring. E is equal to E, move them forward, and now we get a bit of excitement, right? So we see that F is not equal to D, right? F is not equal to D. Let's think back to that naive string matching algorithm that we did at the very beginning. The naive string matching at the very beginning at this point would say, all right, we failed to match, move our J all the way back to the beginning, move our I all the way back to index 2, and start retrying to do matches. That's very inefficient, because as we said also at the beginning, we had noticed that there's this pattern here, AEF, that kind of presents itself here, AEF. How can we sort of programmatically make use of it? Well, we can say, hey, these two letters, I and J, or the letters of these two indices, I and J, don't match, right? F is not equal to D. But J is greater than 0, right? J is not the first letter in the match, J is not the first letter in the substring. So we might have a pattern here that we can exploit. So we're going to say, go to the previous letter right before the J. So we're going to temporarily move J here. See whatever the pattern was that matched this letter here, E, which was at index 1, which once again, I'll repeat it, this meant that there is a prefix AE ending at index 1 that matched a suffix here of the same amount of letters. So we're going to say, go to index 1. So grab this J and go all the way to index 1. And now go to the letter right next to that, because we know that this AE here matches this AE, and we failed at the next letter after that, and see if this letter matches against our letter, right? So what did we do here? Again, to repeat it, we were here, F didn't match against the D, so we're going to say, hey, J, go to the letter right before. Here, we know that we were good. We were still good when our I was one letter before, right? We were still good. So here, we're still good. What was the pattern? We know that if we go one to the right, then the pattern fails. We stop matching. So when did we previously have a pattern here? Oh, it was at index 1. So let's go to index 1. Well, that means that this index 1 here matches here. Like these two letters here match these two letters, right? So now we're going to say, okay, let's see the letter that comes right after it, which would be the potential match against here. So let's move the J here. And here, ta-da, we have a match, right? AEF. So what that allowed us to do is it allowed us not to have to move the I index at all, and only have to move the J index a little bit, and to keep finding a match, right? And so now we're going to move the I one to the right, move the J one to the right, and we can keep going on with our match because we exploited this pattern. So now this is going to become more and more apparent as we continue with the example. A is equal to A, right? Awesome. So now we've got this match so far with our two strings, right? So now we're going to move our I to the right. We're going to move our J to the right. E is equal to E. Great. Move our I to the right. Move our J to the right. And here, F is not equal to D, right? So what do? We're actually exactly in the same situation that we were in like a minute ago, right? But what do? We say, okay, F didn't match D. What was the last character where J was a match? It was here. We know that the character immediately after here didn't match. It failed, right? F and D failed. But so here, the character right before, where did we have a pattern? At index 1. So go back to index 1. At this point, if we were to move I to the left, we know that we're good so far. We've got a match because this is a pattern with whatever we had, the letter that we have before the letter that we had before the failed match here. So move our J one letter to the right of the pattern AE that matched the pattern where we just before the letter that we failed. This F here is equivalent to this D here. Let's see if this F matches, and it does. F and F match. So now we can move our I to the right, and we can move our J to the right. And so now we've got this as the sort of match so far. Awesome. Okay, let's keep going. A matches A. So we're going to move I to the right, and we're going to move J to the right. E matches E. So we're going to move I and J to the right. D matches D. Now this D is finally not causing us problems, so we've got a match here. Keep moving forward, right? So grab our I and our J. A matches A. E matches E. F matches F. A matches A. E matches E. We're almost done, and then boom, we get to another failure. D is not equal to F, right? D is not equal to F. So what do we do here? Again, take a step back, realize what we've done so far. We've said this entire substring here, right before our point of failure at the F, matched, it matched, where did it match? Here, AEF, AED, AEF, AE. This is what it matched, right? Let's go to the letter right before our point of failure. Right before F, we've got an E here. Did we have a pattern matching this E here? We did. We've got an index 4 here. So go all the way back to index 4, which is right here. This E. This tells us that these 5 characters here are a prefix just as they are a suffix for this big substring, right? Therefore, if we bring our J right here, it's the same thing as if we bring our J right here, right? Like the 4 characters before this E are the same as the 4 characters before this E. Now we know that right after this particular E here, we've got a point of failure. This F just doesn't match this D. But let's check what happens right after this E, which is exactly this pattern here is equivalent to this pattern, right? So we go here, go to the letter right after it. So this D here is equivalent, sort of, to this F, right? Compare this D to the letter at index I, and we've got a match. D is equal to D. So now we can move our J forward by 1, we can move our I forward by 1, and I really want to emphasize here, what did we accomplish? Well, our I didn't have to move back to the beginning or to the 3rd or 4th character at all. So far, our I only has moved forward, and our J didn't have to move back that much, right? It took advantage of these 5 characters that we had previously recognized. So now we're going to wrap up this algorithm. We're going to see that A is equal to A. So we're going to move to the right, move to the right. E is equal to E. So we'll move to the right, move to the right. F is equal to F, move to the right, move to the right. A is equal to A. E is equal to E, right? I'm speeding through this now. F is equal to F, and then A is equal to A, right? And then here, this would be an interesting, and so at this point, right, we would say, oh wait, J is at the very end of the substring, so we're done, we've got a match, and we can give our answer, which is true, right? Now, the interesting part here is to see what would happen if we had, let's say, a C at the top, right? Imagine we had a C at the letter I rather than an A. At this point, we would have said, hey, J is an A, I is a C, we have a failure. We know that leading up to the failure, everything was good. So let's go to the character right before it, the F, right? Let's see what pattern matched here. It was, or if there was a pattern, it was at index 2. So if we bring the J all the way to index 2, which is right here, right, then we know that the three characters here, AEF, are sort of equivalent to AEF at the end here. So let's look at the character right after. This character is going to be kind of equivalent to this character. Compare it. We've got an A against a C. They're not a match, so don't have anything there. Let's see if we still have a pattern that we could take advantage of. Maybe we have a pattern that we identified in our substring. So let's look at the letter right before the point of failure, because again, this A was the new point of failure now, this A, right? We know that leading up to that A, AEF, this was fine. It matched these three characters here, AEF. So let's look at the F. Let's look at if this F has a pattern. So we're going to say, does this F has a pattern? Nope, it's a -1, so we're just going to bring J all the way back to the beginning of the array. And you can kind of see how we're going to do this programmatically now, because we would actually bring back J to -1, and then we would say, hey, look at the character right after that, which would be A. And that's it. This is how the Knuth-Morris-Pratt algorithm, or KMP algorithm, works. Before we dive into the complexity analysis portion, I do want to say that you may have seen this algorithm implemented in a couple of different ways, where instead of -1s, you've got zeros. Basically, like, all the values in this array are +1. I actually think that it's a bit more intuitive, at least to me, to have these -1s and to have these numbers here match exactly the previous index where the pattern sort of like ended. But they're all sort of equivalent, and you can kind of work with whatever you find more intuitive. Okay, so now let's quickly talk about the time and space complexity, because this is obviously really important for this algorithm. So the space complexity is pretty simple. The space complexity is going to be O of, and we'll call it M, O of M space, and that's going to be, M is going to represent the length of our input substring, or potential substring. And the reason we've got O of M space is because we're building a table of M length, right? This table, the pattern table, and that's it. We're not building anything else. We're not, using recursion. We're not doing anything fancy. That's all the space that we need. Now, in terms of the time complexity, it's going to be O of N plus M time. We said this at the beginning, right? Where M is the length of the input potential substring, and N is the length of the main string. Now, why is it O of N plus M? Well, the first part of the algorithm, where we build the pattern, is going to take O of M time. And we'll explain why that is in a second. The second part of the algorithm, the actual searching in the main string, is going to take O of N time. And we'll explain why that is in a second. So you can imagine that we've got these two parts, these two sort of independent parts in the algorithm, O of N plus O of M, O of N plus M. Now, why does this take O of M, and why does this take O of N? Well, when we traverse our pattern and we build it up, right, we do at least one pass through it, right? Oh, that's for sure O of M. But there were a few times where, we had two indices. We had, like, I and J. Our I never moved back, right? Our I always moved forward and eventually got to the end. Our J was the kind of tricky one, and this J here is bugging me. Let me make it prettier. Our J was the, well, this one's not that pretty, but whatever. Our J was the tricky one, right? our j was the index that was kind of moving forward and then moving back, and then moving forward again, and then moving back. The best way that you can realize that this is O of m time, and it's because it's bounded by O of 2m, is because any time that j moves forward, I also moves forward. Remember, every time that j moves forward, I also matches j. And sometimes when j is at index 0, then and there is no match, I moves forward alone. Whenever j moves back, then I doesn't necessarily move back. But you can imagine that if j were to move back every time, it would eventually not be able to move back or have to move forward again, which would mean that we would have just double the weight for I to move forward, if that makes sense. Because however much we've sort of advanced with a specific sub-match, j can go back at most that length, and then it has to sort of start moving back forward. And so you end up with a time complexity here that's bounded at O of m, or O of 2m, which is going to be O of m. And then very similar sort of rationale can be used for the main string match. The I index, which started at 0, never moved back. It only moved forward, right? It moved forward when it was equal to the j index, or it moved forward when there was no match and the j index was at index 0. And it was like, okay, we're just looking for a new match, right? The only time that I didn't move was when our j, which was, somewhere in the substring, kept moving back, right? And again, you can kind of imagine that we can only move j back so much before it has to start moving again and move again with I, right? And so if we make, 5 steps forward with j and I, and then we make 5 steps back with j, we can't make any more steps back. We can make at most 5 steps back. And then if we make 5 more steps forward, we won't be able to make any more steps back, right? And so that is why the algorithm here is going to be bounded by O of 2n, and therefore O of n time. And then you add the two together, and you've got O of n plus m. So that is it for the Knuth-Morris-Pratt algorithm, KMP algorithm, really cool algorithm. Let's dive into the code walkthrough now to see what it looks like. All right, so we've got our Knuth-Morris-Pratt algorithm function defined. It takes in a string and a substring. And the first thing that we're going to want to do is to build our pattern using just the substring. So we're going to write a helper method for that. We'll declare our pattern variable, and we'll just make a call to our helper method called buildPattern, passing in just the substring. Now, before we dive into buildPattern, we can already write the second and last line of this main method, which is just going to be to return a call to another helper method that we're going to have, which is going to be called doesMatch. And this helper method is going to take in both strings as well as the pattern, and it's going to make use of the pattern to find the substring in the string. So let's dive into build pattern. So build pattern, taking in our substring. Build pattern is actually going to look pretty similar to doesMatch when we both implement them. Build pattern is going to first initialize the pattern, which is that table that we built, that one-dimensional table, basically an array or a list, that's going to hold all the indices of the sort of patterns being recognized. And we'll initialize this to -1 for all of our letters in the substring. So we'll say pattern equals -1 for I in substring. Then we're going to initialize our two indices that we move through the substring. So remember j and I. J is going to be equal to 0. I is going to be equal to 1. And so long as I is less than the length of the substring, then we can do some stuff. We can try to recognize patterns, compare letters. While I is less than the length of substring, we check if the two characters at indices j and I are equal to each other. So if substring at index I is equal to substring at index j, what happens if they're equal? Well, remember, that means that we've identified some kind of pattern. So we can say pattern at index I is just going to be equal to index j. Because remember, wherever index j is, that means that we've got a sort of prefix in the current substring bounded by I. We've got a prefix ending at j that is also a suffix ending at I, right? So pattern of I is going to be equal to j, and we're not going to forget to increment our two indices. So I plus equal 1, j plus equal 1. Now, if the two letters aren't equal to each other, but j is greater than 0, that means that we might have a pattern to look into. So we're going to say j is going to be equal to pattern of, and this is where it's a bit tricky, pattern of j minus 1 plus 1. So why j minus 1? Remember, we're saying at index j, we've got a failure. Up until index j minus 1, we didn't have a failure. We had things that were equal to each other. So go to the letter, or go to the index j minus 1, the letter right before, that was fine. Check what the pattern is. Go to the index of that pattern, which should be the end of a prefix that is also a suffix, right? If there's a pattern, when you go there, we should still be fine, and then go to the letter right after that, so plus 1, to see if there's a match there, right? And going back to the conceptual overview at this point might be a good idea, just to make sure that you understand this line here and why it makes sense. And then finally, if j is equal to 0, then we just increment I, because if j is equal to 0, then we know there's no more pattern before j, and we just have to keep moving forward to find other matches. And then finally, we're going to return the pattern once we're done with the while loop. Now, like I said, build pattern is actually going to look not too different from does match, which takes in the two strings and the pattern. That's going to be the main difference, that it takes in the two strings. We'll initialize I at 0, j at 0. The reason we're initializing I at 0 is, remember, in build pattern, I is still an index in our substring. In does match, and so we can start at index I because we're comparing it, we can start it at index 1 because we're comparing it to j at all times, so we never want to compare two equal letters, right? In does match, we're comparing characters in the two strings, right? In string and substring. So I and j should be equal to each other at the beginning. So long as I plus the length of the substring minus j is less than or equal to the length of the string, this is just a sort of fancy way of stopping in practice when we arrive at a point when we know that we don't have enough letters left in the string to be to find the substring. So we can do a sort of simple computation where we say, hey, we're at index I right now. If you take the length of the substring minus however far we are into the substring plus I, and you see that we're basically at the length of the string, then there's no more point in looking because we know that we're done. This isn't really necessary, sort of just a nice little optimization practice. You can imagine that if you're dealing with a substring that is 98 characters and a string that is 100 characters, if you get to character number 3 in the string and you have to restart a match, well, then you can basically stop because you're done. So here, if string at index I is equal to string at index j, substring at index j, then what are we going to do? Well, we're going to do a couple things. First thing we're going to check is, are we actually done with our substring? if j is equal to the length of our substring minus 1, then we can return true because we are done and we have found a substring in our string, right? We're saying the two current characters are equal to each other. J is the last character in our substring. Okay, cool, we found the match. Otherwise, just increment both indices, right? If we're ever at a time where the characters are not equal to each other, but j is greater than 0, then this is going to look very similar to build pattern, right? We're just going to say j is going to be equal to pattern of j minus 1 plus 1. Whoops, plus 1. Again, why are we doing this? We're saying, well, up until now, string of I was equal to substring of j. Suddenly, we had a failure, but j is greater than 0. So we know that leading up to j minus 1, we were doing fine. Let's look if j minus 1 had recognized a pattern. If it did, go back to where it had recognized the pattern, go to the letter right after that, and see if that letter matches string of I. And here, by the way, we're going to just go back up in the while loop, of course, and then continue on like that. Okay, so I'll just reiterate that one last time because this is the really important part. String of I is equal to substring of j, great. If it's ever not equal, and j is greater than 0, because if j is equal to 0, then there's no more pattern before that we can go to. We just have to keep moving I forward to find more matches. But if j is greater than 0, we know that leading up to j, so up until j minus 1, things were fine. So let's look if at j minus 1 we had identified a pattern. Let's go back to the whatever pattern we had identified. And by the way, if this is -1, great. We'll go back to -1 plus 1, so 0. But otherwise, just go back to the pattern, right? Go one letter farther than that pattern, because at that pattern, we're still good. We have some kind of match. Go one letter forward, and then go back up in the while loop and check if the characters are equal to each other. Okay, and then else, if j is equal to 0, then you just move I forward. And finally, we can just return false here. Because if we never hit this line, or this line 26, if we never satisfy this if condition on line 25, and we get out of the while loop, then we haven't found the string and we can return false. And that's it. Build pattern is going to run in O of m time. Does match is going to run in O of n time, where m is the length of the substring, n is the length of the string. And that's going to give our algorithm a total runtime of O of n plus m time and O of m space, because the pattern takes up m space, right? It's an array of length m. So that's it for the Knuth-Morris-Pratt algorithm, the famous KMP algorithm, an extremely difficult algorithm, but one that is really cool. I think it's awesome to really understand it. Once it starts to click, it's really pretty awesome, and you realize just how ingenious of an algorithm it is. And it's just always great to be able to know that in an interview, if you have as part of another problem you have to string match or something, you can know that the optimal string matching time is not O of n squared or O of n times m, it's O of n plus m, because you could implement something like the Knuth-Morris-Pratt algorithm. That's it for the video. Hopefully this was helpful. I'll see you in the next one.